Unit 4 is all about integration or anti-differentiation. We're going to work through how to integrate in more complicated ways other than just using the power rule, which is the main way that we were integrating in Unit 3. We're going to talk about Riemann sums and definite integrals. We're going to work through the fundamental theorem of calculus and the second fundamental theorem of calculus and talk about average value. We're going to look at rate graphs. We're going to find the area between different curves and the volume of solids with cross sections. And that's where we're going to learn about the disk and the washer method. So there's a little overview. What we're going to focus on in this lesson is using the idea of the chain rule and how does the chain rule in reverse, so to speak, work with integrating. And we're going to tie that also directly into the idea of U-Substitution. So real quickly, pause this video, work through the two derivatives in this warm-up and see if thinking through those can help you come up with the integrals for 3 and 4. Go ahead and pause the video. So on number 1, the power rule would bring that 4 forward. That 4, after it came forward, would divide out with the denominator. So that would become 1 plus 5x to the third. And then the derivative of the inside, using the chain rule, would be 5. Similarly, on number 2, the derivative of sine is cosine. So cosine of 1 plus 5x, and the derivative of the inside is 5. So here's what I want you to see. Looking at number 1 and looking at number 3, the thing that we're integrating in number 3 is the answer to number 1. And think about what integrating is. It's the opposite of differentiating. So if you can notice that, okay, this looks like 5 in the front looks like the derivative of the inside. So how would this change? Well, it would change because I'm going to add 1 to that exponent and divide by 4. But what would that look like in the original function? So I could tell based just on looking at number 1 and number 3 that this is going to go to the 4th power plus 4, 1 plus 5x. That's just using the power rule. Now, something we have to understand is where does this 5 go? What's happening with this 5? So this 5 comes from using the chain rule, right? That's the derivative of the inside. And when we use the chain rule in reverse, we're not going to take the derivative of the inside. So that's going to go away because we are integrating. The 5 is going to go away with that dx because we're undoing the chain rule. So the chain can just remove that away. And then make sure that you don't forget your plus c. So number 4, again, here is what we're integrating. So we kind of can cheat and we know that the answer is going to be sine of 1 plus 5x. But you have to understand that, wait a second, there's an extra 5 here. What's happening with that 5? That 5 is the derivative of the inside. So when I integrate, I'm undoing the chain rule, which means I no longer need to take the derivative of the inside, right? I'm working backwards. So that 5 is just going to go away. You can almost think of it as in the dx, the integration part is getting rid of that 5. And then, of course, we have to have our plus c. So think about what we did to get from 3 back to number 1. Think about what we did to get from 4 back to number 2, because these are inverse operations and we're basically getting rid of something. We're undoing the chain rule. And when we when we perform the chain rule, we hook on or we attach the derivative of the inside, which in both these cases is 5. The derivative of 1 plus 5x is 5. So that is being hooked on when we perform the chain rule. So when we are undoing the chain rule, so originally we hooked on the derivative of the inside function. When we're integrating and we're undoing the chain rule, we need to unhook the derivative from each side, from the inside of the function. So the dx basically unhooks that. It allows us to get rid of it because we're undoing the chain rule, which means we get to get rid of that piece. So in this table below, you're going to see the integration rules that we learned last class represented in terms of undoing the chain rule. So it's going to have a u in part of it. But I also want to show you, I want to look at number 3 in a slightly different way and hopefully tie together some of what is happening here. So the second half of our lesson is really going to focus on U-substitution, how to do it, step-by-step instructions, but I'm going to explain it to you briefly here to help those of you that aren't seeing the chain rule sort of undoing itself, to help you see it here. So what I want to do is I notice that the derivative of this is 5. So I'm thinking, what happens if I just say that U is equal to 1 plus 5x? So let's let U equal 1 plus 5x. Well, now, if I took the derivative of that with respect to x on both sides, I would get that du is equal to 5 dx, which means that dx is equal to du over 5 if I divide both sides by 5. So now I'm going to rewrite this integral. I had the integral of 5 times something to the third power times dx. So that something that's inside to the third power is now just going to be u. And instead of dx, I'm going to substitute in du divided by 5. So those two 5s are going to divide out. So what I have is the integral of u to the third du, which is u to the fourth plus c. And then we could substitute back in what u was. U was 1 plus 5x, or u to the fourth over 4. 1 plus 5x quantity to the fourth over 4 plus c. So we're going to spend a lot of time on U-substitution, but if on these next 6 examples that we do, if you're really struggling to see how we're undoing the chain rule, know that there's another way to do this, and it's using U-substitution. But if you are able to see the chain rule and sort of in your head do some mental math and manipulation, then you're going to be able to integrate some of these problems more efficiently. All right, so like I said, these are inverse operations for differentiation. So we're saying the integral of the derivative equals the original function plus c, and we're saying that when we're using the chain rule, we're basically just undoing the chain rule. So here in that same box are on the left-hand side is the form that we used with x. On the right-hand side is the form that we're using with the chain rule. So that u prime is the derivative of the inside. But let's actually just focus on some examples here. Okay, so on number 1, I see that I have a composition of functions. So I have 3x minus 1 to the power of 10. I know that based on the power rule, is going to become to the power of 11. But if the chain rule was happening here, I also should have the derivative of the inside. And what is the derivative of the inside? The derivative of the inside is 3. So if this actually said 3 times 3x minus 1 to the 10th power dx with my integral in front, now this would look a whole lot like number 3, the example that we just went over. The problem is there is no 3 there, but 3 is just a scalar. I could put a 3 inside there as long as I put a 1/3 in front, because what's 1/3 times 3? It's 1. So I'm multiplying this integral by 1, and we're allowed to multiply by scalars. So that's totally an acceptable thing to do. So the reason I want to do that is because now this is the chain rule. The derivative of the inside is 3. The outside, if we had added 1 to the exponent, so this is going to become 3x minus 1 to the 11th power over 11. And now that I have this 1/3 in front, 1/3 times that, I guess I could just make that one giant fraction. 1/3 times that, now I'm encompassing for the derivative on the inside, plus c. So this is going to be, what, 3x minus 1 to the power of 11 over 33 plus c. So again, just real quickly, I'm not going to do this on every problem, but if you're having trouble seeing how this works, think about it this way. The integral of 3x minus 1 to the 10th power, whoops, not to the 110th power. If you let u equal 3x minus 1, then du equals 3 dx, or dx equals du over 3. So then our integral would become the integral of u to the 10th power, I guess, times du over 3. And this 3, we could actually just move out front. So this would become u to the 11th over 11, and then the 1/3 comes in. So you can use U substitution, which we're going to talk about in more depth on the back of, well, on the next slide. But you could use that on these problems. The goal is that you eventually don't have to, that you can do the chain rule or undo the chain rule in your head without having to use U substitution. So why don't you go ahead and pause this video and try and do number 2. It's a lot like number 1. It's a lot like number 3 up top. All right, so I'm not going to do it the U substitution way this time. I'm just going to do it using the chain rule. So I'm asking myself, this could be a chain rule problem, but if it was a chain rule problem, I would need the derivative of the inside to show up somewhere. What is the derivative of the inside? It's 5. I can't just put a 5 there without also multiplying by the reciprocal. So what have I done now? I have multiplied this integral by 1. 5 times 1/5 is 1. So now, when I undo the chain rule, this 5 is going to go away with this dx, because really, thinking through that U substitution step, we would be saying du divided by 5 is equal to dx. So that 5 is going to go away. The 1/5 is not. And then I'm going to add 1 to the exponent here. So 5x minus 7 to the 9th power over 9 plus c. So that's going to give me 5x minus 7 to the 9th power over 45 plus c. Now, number 3 looks really different. And in theory, you could just multiply this out and get a polynomial and take the derivative, or integrate using the power rule for each part. But what I want you to notice is that if you look at this piece, what is the derivative of this piece? 3t squared plus 2t. And that derivative shows up right here. So here we do have the chain rule set up. Here is the derivative of the inside. That's the derivative of the inside, which means when I use the chain rule, that's going to go away. Because just like the 5 did on number 2, the dt is going to make that derivative go away because we're undoing the chain rule. We're getting rid of that part of this function. So what that means is all I need to do is integrate t squared plus, t to the 3rd plus t squared using the power rule. So I'm going to add 1. That's going to make this squared, which means I'm also going to divide by 2, and then I'm going to have my plus c. So again, this is much faster than both the option 1 of multiplying that out or option 2 of using a longer version of U substitution. But there's nothing wrong with doing either of those two methods. I'm going to start number 4 by rewriting this using negative exponents. So 4x to the 3rd times x to the 4th minus 1 to the negative 2nd power dx. So then I'm asking myself, what is the derivative of this? What's the derivative of this inside function? Well, the derivative of that inside function is 4x to the 3rd, and I have 4x to the 3rd here. So thinking about undoing the chain rule, that 4x to the 3rd is going to go away when I integrate, because I'm undoing the chain rule that happened when I differentiated. So really, all that I have to do then is add 1 to the exponent of this guy. So that's going to give me x to the 4th minus 1. If I add 1 to that exponent, I'm going to get negative 1. Divide by negative 1, so that's going to be negative, plus c. And you could leave it just like that, or you could rewrite it like that. Either way is fine. All right, go ahead and try and work through 5 and 6. Pause the video. I recommend on number 5 that you rewrite using negative rational exponents. And on number 6, I actually think that there might be a couple of ways that you could go about doing it. So I'm going to pause the video. Go ahead and pause the video. So on number 5, if we rewrite the derivative of the inside, so 4x to the 3rd, is going to go to 12x squared. Now that's not exactly the same as 6x squared, but it's pretty darn close. So that's where I'm asking myself, is there a scalar? Is there something I could multiply by to make this the same? Well, sure. If I multiplied 6 by 2, that would make this 12x squared. But if I multiply by 2, then in front of my integral, I also need to multiply by 1/2. So I haven't changed anything. Half of 12x squared is 6x squared, so I'm all right there. Then I'm going to have everything else the same, 4x to the 3rd minus 5 to the negative 1/2 power dx. So now this 12x squared is the derivative of the inside of those parentheses, which means when I integrate it, that inside derivative is going to go away because I'm undoing the chain rule. So what's left? I'm going to have my 1/2. I'm going to take 4x minus 5, and I'm going to add 1 to that exponent, which is going to make that positive 1/2. And I'm going to divide by that positive 1/2, which means that I'm going to divide by 1/2 or multiply by 2. So this is going to give me 4x minus 5 to the 1/2 power plus c. And somehow I lost my to the 3rd power along the way. Oops, that doesn't look like a 3. There we go. And the beautiful thing here is that you could actually take the derivative of this answer right here and make sure that you did get back to the function that you started with. That's the whole idea here. We're working with inverse operations. All right, number 6. So my first thought is, since we've been doing all this reversing the chain rule, what's the derivative of the inside? Well, the derivative of the inside is 3y squared. Well, I don't have any y squareds here. So this strategy that I have been using where I'm undoing the chain rule, it doesn't seem like it's going to work here. So my next idea is, okay, this is a polynomial that I could expand, right? A binomial squared, I could expand that. That would just give me the integral of y to the 6 plus 2y to the 3rd plus 1, all of that being integrated with respect to y. And then I could just use the power rule. So y to the 7th over 7 plus y to the 2y to the 4th over 2, which is just going to, over 4, which is just going to become y to the 4th over 2 plus y plus c. So something I want to remind you is that just because we're in a section about a certain topic doesn't mean that every problem needs to follow that exact method. So always keep that in mind. Think through your approach before you start doing the math. For 7 through 9, we're going to look at these in more of a trig way. So sine of 4x, again, thinking about the derivative here, if this had a 4 in front, then it looks a whole lot like the chain rule because the derivative of something is sine, but then the derivative of the inside is 4. So I'm going to put a 4 here. I'm going to put a 1/4 here. I'm going to make sure I don't forget my dx on the end. So now the 4 in front and the dx, when I integrate that, the chain rule is undoing that. So what's left is the 1/4 in front. And then what do I take the derivative of to get sine of something? I take the derivative of negative cosine. So I'm going to put cosine of 4x here, and I'm going to just stick a negative in front, and then don't forget your plus c. Number 8, 3 theta cosine theta squared. So what's the derivative of theta squared? The derivative of theta squared is going to go to 2 theta. So I have a 3 where I kind of would like a 2, but I could fix that. What I could do is, so theta squared goes to 2 theta. So if I want a 2 theta to be inside, if I want this to say 2 theta cosine of theta squared d theta, how do I do that? Well, I need to take the 3 out front, and then I can't just multiply by 2 without also multiplying by 1/2. So I could rewrite it like this. And that would give me, so the 2 and the d theta are going to go away together, or the 2 theta and the d theta are going to go away together when we undo the chain rule. So how do I get cosine squared? I get it from, or cosine theta squared, I get it from sine theta squared. The 3 over 2 is going to stay in front, and I'm going to have a plus c. Number 9, I'm going to kind of skip ahead. I'm just going to tell you that number 9 is sine of x cubed. I guess you could put the cubed on the inside, over 3 plus c, and you can look at the worked out solutions if you need more help on that problem, but this video is already getting a little bit long. So let's actually wrap up by formalizing U-substitution and working through a couple of problems on that. So another way of approaching it, like we talked about, is rewriting it in terms of another variable. And we did this already on a different example. So for this example down here, we're going to let u equal the inside function. So I'm going to let u equal x minus 1, which means that du is just going to be equal to dx, which allows me to then rewrite this as u to the 1/2 du, except I need to deal with this x. This is sort of the more complicated case when we have an x that we have to deal with. But I could just solve this. X is equal to u plus 1. So this is going to become, I'm going to just draw an arrow. I didn't save myself enough space. The integral of u times u plus 1 times u to the 1/2. So u to the 3/2 plus u to the 1/2, all with respect to u. So now we can integrate using the power rule. So I'm going to get 2/5 times u to the 5/2 plus 2/3 times u to the 3/2 plus c. And then after that, I'm going to plug back in my x minus 1. So u equals x minus 1. That's going to give me 2/5 times x minus 1 to the power of 5/2 plus 2/3 times x minus 1 to the power of 3/2 plus c. So what you're basically doing is using u equals something to simplify the problem so that you can just focus on the integration and then at the end substitute that u back in. So the steps of this procedure: determine the inside function. That's what you're going to want u to be. Most of the time u is going to be the inside function. Set u equal to that. Take the derivative so that you have du in terms of x and dx. Sometimes you're going to need to solve for x. Sometimes you won't. Then plug everything into your integral and integrate in terms of u, and then substitute your u back, your u equals whatever in terms of x back in so that your final answer is in terms of x. All right, let's look at these last 5 problems. We may not have time to do all of them, but let's do what we can. So I'm going to set u equal to 2x plus 2x minus 5, so du is going to be 2x dx, and then I'm going to solve both of those for du and dx. So now that I have all that, I'm going to substitute everything back into the integral in terms of u. Now, because I don't like having these fractions inside my integral, I can take both of these 1/2s out and just put 1/4 in front of the integral. And then I can multiply 1/2 times, u to the 1/2 power times u plus 5 and rewrite that. So the integral of u to the 3/2 power plus 5u to the 1/2 power du. And now I can integrate using the power rule. So I'm going to have 1/4 times 2/5 u to the 5/2 plus 1/4 times 5. I guess I'm just going to stick the 5 up top. Times u to the 1/2 plus 1 is going to be 3/2. So 2/3 u to the 3/2 plus c. And then I'm out of space, so I'm going to try and squeeze on the bottom this final answer in, back simplified and with 2x minus 5 substituted in for u. And there it is. On 11, I'm going to rewrite it, and then I'm going to let u equal 2x plus 3. So go ahead, pause the video, do that, and then work through this. So here we are. So we can rewrite this as the integral of 2 times x, which is u minus 3/2 minus 1, times u to the power of negative 1/2 times du over 2. But that's actually going to simplify, and I'm going to take 1/2 out. So that's going to give me 1/2 times the integral of u minus 4, if I simplify that first part, if I simplify 2x minus 1, times u to the negative 1/2 power. And then that's going to simplify again. So I'm going to write that next step down. So that's going to give me 1/2 times the integral of u to the 1/2 minus 4u to the negative 1/2 du. Then I can use the power rule to integrate. That's going to give me 1/2 times 2/3 times u to the 3/2 minus 1/2 times 4 times 2 times u to the 1/2 plus c. And then if I simplify that and substitute back in what u was, I'm going to get 1/3 times 2x plus 3 to the power of 3/2 minus 4 times 2x plus 3 to the power of 1/2 plus c. And I'm going to erase this middle step because I'm obviously running a little bit low on space. Go ahead and pause this video and see if you can work through number 12. So let u equal 5x squared. So du is 10x dx, which means that dx is du over 10. So now we can substitute all of that back in. So that's going to give us the integral of x times the cosine of u times du over 10x. So these x's are going to divide out. And I'm going to move 1/10 to the front. So I'm going to have 1/10 times the integral of cosine of u du. Well, the integral of cosine is sine, so I'm going to have 1/10 times sine of u plus c, but instead of that, I'm just going to substitute back in what u is, which is 5x squared. So 1/10 times sine of 5x squared plus c. Number 13 says if f prime of x is that function and f of 2 is 5, determine the equation of f of x. So pause this video and see if you can do that. I'm going to work through it as well. So there's the worked out solution for 13. You're going to use U-Substitution or potentially just using the chain rule to integrate there, and then you're going to plug in the initial condition to find the actual exact function with no c value. I'm going to fill in the answer to 14, but go ahead and pause 14 and work through it on your own. Then you'll see the solutions, and then that'll be it for the video. So there's the solution to 14. There's a much more detailed version of it if you look at the worked out notes in Google Classroom. So the moral of the story today, we can undo the chain rule in order to integrate, and we can also use U-substitution, where we use the inside function to make that equal u, take the derivative of both sides, and then substitute that back in order to integrate something that's a little bit less messy, a little easier to integrate. Looking forward to working on more practice problems like these in class. See you then.